Good morning, everyone. Today in this slide or in this video, we are going to learn about diameters of bright and dark rings in Newton's ring experiment and the applications of Newton's ring. If you will see my previous video, there I have explained about the experimental arrangement of Newton's ring and the formation of Newton's ring and the condition for constructive and destructive interference pattern. So in continuation with that, this video I have made for the diameters of bright and dark rings. As in the Newton's ring experiment, we observe alternate dark and bright circular concentric rings having the center as dark where the condition of destructive interference pattern takes place. Because where the plano-convex lens meets the glass plate at that particular point, the thickness is 0, and if we substitute the value of thickness 0 in the path difference equation, then we get the path difference equal to lambda by 2, which is a condition for destructive interference pattern, which is explained in my previous videos of Newton's ring. So you can see from there itself. Now in this case, in order to evaluate the diameters of bright and dark rings, what we consider a circular plano-convex lens. This is the dotted line shows the circular plano-convex lens, which I name it as LOL dash, and this circular plano-convex lens is placed on a plain glass plate, that is AOB. Here capital R is the radius of curvature of this plano-convex lens, and T is the thickness of the film at some point P. As we move ahead or as we move away from this point of contact on both the sides, we see that the thickness gradually goes on increasing equally on both the sides. So we take some point P. At that particular point on both the sides P and Q, the thickness is same. From D to O, this is completely twice of R, which is the diameter of this plano-convex lens, which is equal to twice of R. So if I see from the property of a circle, if I apply the property of a circle over here, then property of a circle clearly states that this distance Qn multiplied by Np will be equal to N0 into Dn. Now this Qn is nothing but the radius of the ring passing through the point P, and Np is also the radius of the ring passing through the point P. Dn, capital Dn, is completely twice of R, capital R, which is the radius of curvature of this plano-convex lens. So the distance Dn will be equal to 2R minus T, and N0, this distance is the thickness T. So I will substitute all the values of Qn, Np, N0 and Dn in equation 1. So Qn is R, radius of the ring, Np is again R, which is the radius of the ring, No is the thickness T, and Dn is twice of capital R minus T. Capital R is the radius of curvature of this plano-convex lens. So if I multiply this parameter, so this becomes twice capital R T minus t square. So radius of curvature of plano-convex lens is very high value in comparison to the thickness of the rings. So small t, which is the thickness of the ring, is very small in comparison to radius of curvature of the plano-convex lens. So if I will square the value, that is t square, that value will also be very less in comparison to capital R. So hence we will neglect the term that is t square. So twice RT minus t square will be written as twice RT, where t square is neglected in comparison to 2RT. So from here the equation reduces to the form of R square is equal to twice RT. So from here the thickness of the film we can calculate, that is equal to radius square upon twice R. Radius, that is the ring which is obtained, we can easily determine the radius. So if I will know the radius of the ring, I can know the thickness of the ring at that particular point. So equation 2 gives me the thickness of the rings. So now we will calculate the diameter of bright ring. In order to calculate the diameter of bright ring, we will consider the condition of constructive interference pattern, which is given by equation 3rd. This equation we have already derived in our previous video of Newton's ring experiment. So from there we have taken this equation 3rd, that is the condition for constructive interference pattern. So that equation is 2 mu t is equal to 2n minus 1 lambda by 2, where n starts from 1, 2, 3 and it goes on. Now we will substitute the value of equation 2nd, that is the equation of thickness, in our above stated equation 3rd, the condition of constructive interference pattern. So simply we get the value twice mu r square upon 2r. This is equal to 2n minus 1 lambda by 2, or if I cancel out some parameters over here, my r square is 2n minus 1 lambda r upon twice mu. If nth ring passes through the point P of the film, then r should be the radius of nth bright ring. So my above equation can be rewritten as Rn square is equal to 2n minus 1 lambda r upon twice mu, where capital R is the radius of curvature of plano-convex lens, lambda is the wavelength, mu is the refractive index of the film. So equation 4 is in terms of radius of nth bright ring. Same equation can be rewritten as in terms of diameter, that is dn square upon 4. So dn square upon 4 is twice n minus 1 lambda r upon twice mu, or dn square is equal to 4 2n minus 1 lambda r upon twice mu. This 4 and 2 gets cancelled out. So the diameter of nth bright ring is written as square root of 2n minus 1 lambda r upon mu. That is my equation number 5. So equation 5 is the expression for the diameter of the bright ring of order n in Newton's ring experiment immersed in liquid of refractive index mu. But in our experiment, we have not introduced any liquid in between the plano-convex lens and glass plate. So the film is formed of an air. So for air, the refractive index mu is 1. So my equation 5 is rewritten as dn is equal to k square root of 2n minus 1, where k is square root of 2 lambda r and n is 1, 2 and 3. So from This equation says, thus the diameter of bright rings are proportional to the square roots of odd natural numbers. So in the similar way, we will calculate the diameter of dark rings, and the equation 7 is a condition for diffractive interference pattern, that is 2 mu t is equal to 2n lambda by 2, or I can write it as n lambda, where n starts from 0, 1, 2 and 3. So in the similar way, we will again substitute the equation 2 of thickness in above equation number 7. So my equation reduces to the form of twice mu r square upon 2r is equal to n lambda. 2 and 2 gets cancelled out. So r square is n lambda r upon mu. If nth ring passes through the point P of the film, then r should be the radius of nth dark ring. Therefore, above equation I rewrite as in terms of nth dark ring, that is Rn square is n lambda r upon mu, and equation 8 in terms of diameter is written as dn square upon 4. This is n lambda r upon mu, or dn is equal to square root of 4n lambda r upon mu. Thus, equation 9 is the expression for the diameter of bright ring of order n in Newton's ring experiment immersed in liquid of refractive index mu, but in our case it is an air film, and for air film refractive index is 1. So diameter of dark ring is equal to k square root of n, and where k is square root of 4 lambda r, and here the value of n starts from 0, 0, 1, 2 and 3. So in this way, the diameter of dark rings are proportional to the square root of natural numbers, whereas the diameter of bright rings are proportional to the square root of odd natural numbers. So now we will continue with this, the applications of Newton's ring. That is this experiment. By using this Newton's ring experiment, we can determine two important parameters. That is, first is the wavelength of sodium light, and another is the refractive index of an unknown liquid. So in order to determine the wavelength of sodium light using Newton's ring, we will perform this experiment in the same way as it is shown in our previous videos of Newton's ring experiment, where the plano-convex lens is placed on the plain glass plate and r is the radius of curvature of the plano-convex lens, and lambda is the wavelength of light used. Now here we will consider the diameters of dark ring. We can also consider the diameters of bright ring, but for this I have considered the dark ring. So if I determine two dark rings, that is I denote it by dn as the diameter of nth dark ring, and dn plus p is the diameter of n plus pth dark ring. So using the equation of dark ring, dn square is 4n lambda r, that is my equation 1, and dn plus p square is equal to 4n plus p lambda r, where p is an integer. That is my equation 2nd. If I subtract equation 1st and 2nd, I will get dn plus p square minus dn square, bracket close air. I am writing air here because the medium over there is an air film, not any liquid is not immersed between the plano-convex lens and glass plate. So the film which is formed is of an air. So this is equal to 4n plus p lambda r minus 4n lambda r. If I open this bracket, so 4n lambda r gets cancelled out. So final outcome comes out to be 4p lambda r. So from here I can easily write down the wavelength formula. So wavelength of the sodium light will be dn plus p square minus dn square upon 4pr, where p is an integer, r is the radius of curvature of plano-convex lens. So once we know the diameters of the rings, we can easily calculate the wavelength of an sodium light. So next application is the determination of refractive index of a liquid. So in order to determine the refractive index of a liquid, we have to perform these experiments in two parts. First is, we will perform this experiment as it is previously stated, that is, the plano-convex lens and glass plate is placed and the rings are formed, or the film which is formed is of an air. So in the same way, we will determine the diameters of nth and n plus pth dark ring by using traveling microscope, which is my previous slide, that is diameter of nth dark ring is 4n lambda r and n plus pth dark ring is 4n plus p lambda r. So dn plus p square minus dn square of an air is 4p lambda r. That is my equation 1. Now what we will do? We will introduce the liquid whose refractive index is to be determined in between the plano-convex lens and glass plate without disturbing the whole arrangement. Only we will introduce the liquid between the plano-convex lens and the glass plate. Again, we will observe in a traveling microscope the rings are formed, alternate dark and bright rings are formed. So in the same way, we will again calculate the diameters of nth and n plus pth dark ring. But now here we have introduced the liquid between the glass plate and plano-convex lens. So the diameter of n plus p square minus dn square instead of an air in equation 1. Now I will write it here as a liquid and I will get the equation. This is 4p lambda r upon mu. In equation 1, here in the denominator we do have the refractive index mu, but for air mu is equal to 1. That's why we get the equation as 4p lambda r. But in equation 2, here we are considering a liquid. So for liquid, refractive index is to be determined. So I will divide equation 1 by equation 2. So I will get the refractive index of an unknown liquid, that is dn plus p square minus dn square of air divided by dn plus p square minus dn square of liquid. So if the refractive index of the liquid is high, then the diameters of the rings obtained will be contracted. So here are these are the two applications of a Newton's ring experiment. Thank you.